right, so let's talk about bond dipoles. So the dipole moment is a quantitative way. Instead of us talking so qualitatively with the different types of polarities, this is a quantitative way of describing the polarity of the bond. A dipole is a piece of material. It's kind of like a rod. You can use a rod stick, and it's got a positive and a negatively charged end. And I can actually use this dipole to measure the strength of that bond. Okay? So the dipole moment, symbolism mu, is the measure of that bond polarity. How much pull is it going to be? Here's my equation for my dipole moment. So the dipole moment is equal to Q times R. So what is Q? So Q is the size of those partial charges. So it is how big of a partial charge is it? And that is going to be directly proportional. So if the partial charges are really big, then my bond polarity is also going to be really big. Okay? And then the next thing is the distance between them. So the distance between them, the bond dipole, is directly proportional also to the distance. So my dipole moment is going to be related to the size of the partial charges and the distance. Now, you might have seen this as Coulomb's law before, or think it is that. It's not related to that. And dipole moment is usually measured in dBs. Now, you're not going to have to actually do the math or anything. I just want you to be aware that there is a quantitative way to measure bond dipoles, okay? So instead of just categorizing which one it's in, I can actually get a specific number in dBs to be able to really compare the different bonds. Another thing that I might want to talk about is I might want to talk about the percent ionic character. Oops. So I might want to also talk about the percent ionic character. So this is the percentage of the bond's measured dipole moment to what it would be if it was full ions. So I can actually go back to here. So if the electron difference is really high, then this is going to be a high percent ionic character. This is going to be closer to 100% ionic character. Here, where they're sharing equally, this would be closer to a 0% ionic character. So as I go from left to right, my percent ionic character is going to increase. All right, so let's look at a practice problem that kind of puts this all together. So this problem says determine whether an NO bond is ionic, covalent, and when you see just covalent, that's pure covalent, and polar covalent. So ionic, pure covalent, I'll just write that in there for you, and polar covalent. So first let's say, okay, let me look at where NO is on the periodic table. I don't want you to go and look at the chart with the electronegativities. I want you to be able to just think about this in your head. So if I go to my periodic table and I find N and O. Okay, here's N and here's O. So, are they the same? Are they the exact same element? No, one's N and one's O. So for it to be pure covalent, it has to be the same element. So, oops. So that's not the case. So ionic. Ionic was if it's a metal and a non-metal. Well, what are these? They're both on the right side, so they're both non-metals. So this has to be a metal and a non-metal. Well, that's not the case here. So the only thing that's left is polar covalent. Now, you might be wondering, okay, well, I thought you said if they're touching each other, they're pure covalent. Yes, most of the time if they're touching each other, they're pure, non-polar covalent. If they're touching each other, most of the time they are non-polar covalent. This is one of the exceptions to the rule, and that's why I didn't give you non-polar as a choice, okay? So sometimes it's hard to tell if it's gonna be non-polar or polar. Those two can kind of get a little tricky. And so based on the question, you notice I didn't ask you to choose between those two, because you could only choose between nonpolar and polar covalent if you had the exact numbers. But in this case, we're just using the definitions of my terms to figure out if it's going to be an ionic bond, a pure covalent bond, or a polar covalent bond. All right? So now that we've talked about the definitions and got our basis, now we're going to get to the fun part of this chapter. Now we're going to start drawing Lewis structures. So in the next lecture, we're going to start doing it. We're going to start drawing our first Lewis structure.